All right, hello everyone. My name is Daniel Smith. I'll be your instructor today. So I'm actually from not the MSKCC or even New York. I'm from at an institute called the Computer Sciences Software Institute, or MOLSI for short. So I do a lot of Python development and interactions with scientists every day. So hopefully today we'll talk a little bit about how to do documents and give you some clean code. So I understand that this is probably the first time this has been taught, so we'll actually edit this ever so slightly so that we'll actually talk a little bit about how to build modules, and then the process of building modules, in this particular aspect. So a little bit about me, just so you know, I've been programming on and off for 7 years, I guess about the past 6 years straight. Mostly focused on Python, C++, and general high-performance computing. So always in the scientific domain as well, mostly in chemistry. So I do a lot of things like I work on NumPy, for example. If you use the Einstein function, I wrote a good chunk of that these days. I also do Site4, which is a pretty big open source chemistry program. If you guys are not familiar with that, that's okay. But in general, I do a lot of Python workflows and large-scale databases. So how do I run maybe thousands or tens of millions of computations on hundreds of thousands of cores and orchestrate this in such a way that it's usable to everyday scientists? Is really kind of what I'm focusing on these days. And also, I've been a software professional instructor for the past 4 years. So doing things like this is kind of my day job in some ways. And so I'm currently at the Computer Sciences Software Institute. Just if you guys have not heard of us, which you probably have not, we are kind of a unique institute funded by the National Science Foundation, where our job isn't really to create like a new piece of software that is user-oriented. We're not trying to compete with all the software in our domain. Instead, what we're trying to do is we're trying to serve and enhance the community through education, things like schema, so we can do interoperable programs and like. So this mostly focuses on quantum chemistry and quantum mechanics. If you want to know more about MOLSI, please let me know, or you can go to our website at MOLSI if you so wish. Okay. So any quick questions about any of that before we get going? Right. All right, can you guys read this in the back? Good. Good. Okay, so today, if I understand it correctly, and please interrupt me if I'm wrong, you guys have done a little bit about building some functions, and you can do some scripting and the like. Is this true? Okay, yeah. See some nods. I don't see anyone shaking their heads. So this is good. All right. So today what we're going to do is we're actually going to work on building a little module. So far, whenever you have scripts are fantastic if you want to do kind of like one quick one-off things. So if you want to do something very quickly to get some sort of result. But I think most people, what they find is they build lots of scripts. They find pieces that they want to repeat, right? So you have like a function that you want to use in a lot of different places. And so really that's the question that we're trying to answer today. Is how do you build a little library for yourself as you get more and more into your work and find that you need something above and beyond scripts that run through and do a single operation. So to do this, Python has modules. So I was working in Python today because this is actually language specific. If you are in R, R has a very analogous process. And if you want, I can also discuss a little bit about how to do this in R, but it's extremely similar once you do it once. Okay. So the first thing that we need is we need to think of some sort of name for our package. So there's things like NumPy and Pandas in Python, which you likely use, and so analogously we need to come up with something to start with. And usually what we can do is usually take a vote. We can do some sort of like math algebra or word counting programs. Anything on math algebra? Got 2, 3, okay. 4, okay. All right, 4. Word counting and word manipulation. 1. 2, okay. Any other topics? We can do anything as long as it's relatively simple. Okay, Okay, so a little bit of algebra math is. So in that case, let's go ahead and make a directory called algebra, because we're going to be not very creative and call our program algebra to very precisely elucidate what it does. Okay. So now that I'm inside this folder, I need to realize that my package structure has two levels. So first of all, whenever I have something like NumPy, NumPy is an entire self-contained package. And once you have it on your computer, everything that you need to run NumPy is inside the single folder. But whenever you're building out a package, you actually need one folder structure below that that holds all kinds of things, like what's your documentation, what's your README, etc. So you always want to have kind of like this interesting nested folder structure. And historically, what we want to say is have the same name twice. And so what the base folder is going to be all of kind of like the extra information about your package, while this internal package is going to be where all of the content that you want to replicate goes. And so whenever we build these packages and we have this defined, we usually want to, we have some sort of function in mind. So when I think of algebra, what's a quick function that I'd like to have repeated?
Sum.
Sum. Okay, great. All right, so let's do a sum. Okay. So the first thing we need to do is just like before, we need to make a Python file, and let's just go ahead and call it sum.py. And so when I write this function, I can call it anything, but I might want to call it sum here as well. And what should this function take as an argument? So two numbers. So are you just going to just sum two numbers? Or more? So you want a list of numbers. Okay. So have you guys seen the star operator in Python? Something like this. Okay. So in that case, let's just do two numbers from now, and then we'll go back and rewrite our function to be a bit more flexible in the future. So I can do num1 and num2. And what do I need to write here to give me back my sum?
Sum equals num1
Yeah, just something like this, right? So something very, very basic. All right. Okay. So now I have my very first module. So each one of these is going to be a module. It's called sum. It has a function that I want to reuse all over the place. Now I need to do something very Pythonic, and what that means is I need to create something called an init file. And so what an init file is basically, until you have an init file, Python doesn't know, like it's just like a file structure of Python. It doesn't understand anything about this. And so if I have something called init, and you have these dunder inits, or this double underscore on either side. And you may or may not have seen this in Python before, but anything that has like these double underscores is kind of like these special things within Python. So this is just something that you get used to. And so once I build this guy, and so this is kind of like, what is it going to be included into my package? And so here, what I want to say is from dot import sum. Okay. And so you have likely not seen this dot import before because this is canonical Python importing. But with modules, we need to say where are we coming from, right? Because there could be, so for example, if I name something called NumPy and I put it into this folder, how would I know what numpy to pull from? And so the from.import sum says, from this folder, import the sum function. All right, so now I actually have a fully functioning package. So if I go one level below, so remember I'm inside my Algebra folder and I want to import my Algebra package. So if I just boot up a Python interpreter and say import Algebra, I can import my function. And so how do you think I would call my sum function? And so you'd be very close, but what you actually get in this particular case is you get the individual module involved. And so to think about this is like it's kind of navigating file structure like through Python. So if I have my algebra and I have the file sum, and then inside of that I have the function sum, I need to say basically algebra.sum.sum. And so you can quickly see that perhaps that we have incorrectly named these things because we made it a little bit confusing on ourselves. And so part of this clean code is trying to realize some of these kind of common errors that people run into and look at solutions for them. So now that I have sum.sum, if I say, for example, 4, 5 and call my function, I will get 9 back. And so this is, in effect, the entirety of Python modules, is you write functions inside files, you import them in various regards, and you can call them from anywhere. So overall, like the hope is that at least getting started into these things is actually really quite straightforward and simple. And what we're going to do over the next couple hours is kind of explore how do we turn something like this into something that's a little bit more reusable and reproducible over time. All right. So at this point, do we have any questions?
Sorry, I still didn't get why you need to choose some of the algebra.
Yeah. So this first thing is saying like I'm going to my algebra package, right? And inside my algebra package, or basically that file structure, I have a file called sum.py. So basically what I'm saying is I'm going to go to the algebra folder, the sum file, and then the sum function.
Oh, so the second sum is the function name, that's why.
Yeah. Anything else?
Go back to the sum.py.
So now if I think about it, what's a better name than sum.py? I want to add something else to my sum function.
Better name for this file?
Yeah, just for this file. Like we don't really want to call it sum. We want to call it something else that includes maybe sum, and maybe you want to do like subtraction or factorial or something like this. Operation. Okay, so instead of calling it operation, can we move it to operations? Plural, because we probably want more than one operation in this. Okay. So now that I've renamed this operations, what else do I need to do?
That's your init file.
Init file. So instead of saying from .import sum, let's say from .import operations. And so now I can say import algebra. I could spell, that would be very helpful. So you can see that I now move this over, and whenever I do this, I think this is a much more logical way of laying this out, right? So instead of saying sum.sum, I have algebra, and if I want some sort of operations, it can be here. So what if we want to write one more function inside of our operations? Anyone think of a good little function to write?
Product.
Products. Okay, so let's do products next. And if you could, please go ahead and try to do this on your own while basically adding this function to your operations file, and then trying to import algebra and run it to make sure that you get the right answer. And usually we have sticky notes, but if you have any issues, just kind of flag me down, and I'm happy to help. Okay, so has everyone approximately gotten the products? Anyone have questions? Sure.
To use to import the package module, do you always have to be on the left side?
Right now, yes. So for right now, you always have to be in that one level down, because Python will always search for your package there. But later, we'll actually install your package so that you can access it from anywhere. So now we have sum and product functions. And so now I'm going to say algebra, operations, I can now get the same thing. Okay, so let's do some little thought exercise stuff. So, for example, when I'm in here, and so if you guys will know this, inside of a terminal, if you have like a dot and you hit tab, you can actually get a list of all the available functions. But if I'm just kind of like a new user, kind of exploring around my code, and I'm going to need to know, for example, like what does product take, right? So I need at some point some kind of help function to give me an idea of what's going on there. So currently, if I run, for example, so if I run help on this, all I get is a little string like that. And so in a lot of ways, is that super helpful? I mean, if I have something like product, then yeah, it's probably not bad. But if I have something like my very special function, you're going to need a little bit more. And so what's nice about Python is we can actually do documentation on these individual functions really quite simply. And so what we can do is we can go to each of our functions and add a string inside triple quotes below the function. And so here, I can write anything that I wish. I can say like a very simple sentence, like this takes the sum of two numbers, or I can actually write paragraphs and paragraphs here, and so that I can get it from help always. And so probably the one question that you have is that why would you want to do this if if this little module is just for you? So for two reasons. One, I think that modules are rarely just for you. You'll likely want other group members or perhaps other members in the community to eventually use this little piece of code. And two, I can't stress that this is definitely for yourself as well. I think for people who program more and more, you will find that you start having tens or hundreds of functions that you write. And keeping all those track will become really quite a trial. When, for example, just a couple sentences real quick underneath there to describe what this particular thing does is going to be incredibly helpful to yourself later on. And so what's nice now is that I go back and I run help on my module. First of all, I'll get saying that the name of my package is going to be Algebra, and that inside of this I have something called operations. And so a user can, or yourself, can programmatically explore down through the levels. And so for now, if I run help on my operations, I actually see that I have these nice functions. So I have product and sum, and I give a very small description of each one does. The nice thing about help is it has really good Jupyter integration. So if you're in a Jupyter notebook, writing help there, you'll get very similar strings, even more developed in a lot of ways. To the command line, you get help there. And if you're even programming, you get to see that little string of code telling you what this function does, which is very useful. In addition, depending on how far you want to go with this, if you want to do, for example, like documentation, like you see like NumPy's documentation, for example, or Panda's documentation, you have those big blobs of text showing you like what this project does and all the functions involved. And if you actually look into the code, what those are just like this. They are strings underneath each of these functions that are mostly templated with other projects, but at the end of the day, it's just text inside these functions. So across the board, very, very helpful to do, I would say.
Quick question.
Sure.
So this is obviously a simple example, but you're developing more complex functions in terms of like documenting the types of input you're getting and the types of outputs that you're getting. List, or is there standard syntax or packages for that?
Yeah, so there's currently two ways to do this. So a lot of NumFocus inherits from what's known as the NumFile style documentations, which means that you have things like, here's a good example, where you have parameters here. And so, for example, a parameter with the line underneath it can be taken and expanded out to give you NumPy or Panda style docs in terms of all the syntax highlighting and the like. So if you want, you can kind of basically recreate all of your doc strings to look exactly like this. And once you do something more complex, like using Sphinx to build documentations that you find online, it will automatically template it out into a particular style. And if we get enough time, we can certainly go through that today. And if not, feel free to ask me, and I can point you towards some more resources. The other thing that's coming up is actually typing in Python. And so what this means is that this only works for Python 3.6 plus, but you can actually type all of your input and output arguments. And so what this will do is this will give you a lot greater control over exactly what goes into these things. And so with this particular style, it's only enforced in strings and what you're telling the user. So as you know, in Python, I can basically pass anything and anything, and if it works out, it works out. But with actually these type hintings, what I can do is I can run my typical Python program, and it will run as normal. But I can run it under an alternate mode called MyPy, which will actually make sure that all the types are correct going through your entire program. So it really depends on kind of like the level of specificity that you wish. And in general, for right now, for probably another year or two, I recommend doing this. But probably in another year or so, like typing is going to become ubiquitous enough that you get an enormous amount of help out of it. But realistically, what we're waiting for is some of the base packages to get typing in, and then we can slowly move and grow packages from there. Answer your question?
Yep.
Great. So in this particular case, what we have is simply and so you can go on and on like this. And so, again, if you have this, you can easily template it out. And for example, I don't have a good one, but effectively you can automatically generate style docs like this from it. Okay. So now we have a little bit of rudimentary documentation involved. We have a couple functions. But like I said, we have this base folder, and now we want to start doing things with that base folder. So the very first thing that everyone likely needs is a readme.md. And so inside of this, what we're going to use is something called Markdown. And so what Markdown is it's just kind of like any other sort of, I can write some kind of text and it gets marked up so that I get some sort of nice display feature from it. For right now, before we do too many more advanced things, I won't go too much into the Markdown syntax, but there are just Google like Markdown tutorial. They'll give you plenty of guides on it. The reason I like Markdown is there's like 4 actual syntax features involved, so that it's extremely simple to get up and get going. But what it gives is like whenever you're like looking at these things on the web page, it gives you at least some sort of syntax besides just flat text. So it gives you like bold and highlights and code and the like. So really quite useful. So in this readme.md, these can be extremely involved or they can be very simple, but it's usually just to give some sort of hint of what this particular program does, or this particular module. So at this point, we don't know a lot about what our particular module does, and so therefore we will be very generic in return. And so the important thing is not particularly the content of the node, but just simply that we have one of these readmes, and that we'll probably want to extend these out in the future. And I think the other thing was asked was, at this point, our little module can only be used in this base folder. What we would really like is if this module can be used anywhere whatsoever in our Python environment. So to do so, we're going to need something called a setup.py. So a setup.py is effectively a small description of what your package is, what it contains, and how it should be installed. And so you can go through by hand and try to figure out exactly every single part of setup.py. However, I think always the best thing to do is Google Python setup.py example. And the nice thing about setup.py is virtually any example that you run across will be more than sufficient for your needs. So in this particular case, perhaps I might want to use the actual Python documentation, which is always a good source. And so I get an exact little version of what my setup.py is. And so, like I said, these things are kind of formulaic in nature, so they're always good to search for and find. So if we can grab this little guy, just copy and paste. And move them back to our base folder. And paste them in. So again, just going to the official Python documentation, grabbing a version of setup.py, and copying it to setup.py folder. Then, of course, when it comes to the setup.py, we do not actually want to use these particular things because we want this package to be attributed to us. We want to make sure it goes to our email, and the name is going to be, in this particular case, Algebra, or where you decided to name your package. So if you will, go into your setup.py and go ahead and edit all of these lines. And for example, you don't have a URL yet, so you might just want to leave that one blank. So a blank string is perfectly fine. If anyone has any troubles, please do flag us over.
About the first 2 lines.
The first 2 lines. So the first one is what's known as a shebang, which means that if shebang, I don't know why. Yeah. And so what this thing is at the very top is actually a bash specific feature that if I just type, if I had this as like an executable and I ran that, what that would do it would run this entire script with that program. So what's nice about that is it would always run it underneath Python. In general, this is not particularly a required thing on setup.py. It's merely nice. But since the particular one that we copied from, we used it. And the other thing is that distutils is an inbuilt Python package. So there's a little bit of pull between distutils and setup tools. You'll probably find them both in these setup.pys. But just for now, again, it is purely a, this particular part of the code is purely a template that you use without any particular, unfortunately, understanding of exactly what's going on. It's unfortunately slightly more opaque than what we want, I believe. Okay. So now that we have this information filled out, so what we want now is to be able to go anywhere inside of our package and be able to use Algebra. And so if I look up on the internet and I say basically, how do I install Python package? I'm not sure if you're familiar with Stack Overflow, but Stack Overflow is extremely wonderful. But unfortunately, it's giving me answers a little bit more complicated than what I'm looking for. So a quick search on the internet basically shows that maybe I did it wrong or not, but it was more complicated than it was helping. But the magic thing that we're looking for is a pip install -d doc. And so I think one of the good questions is that if you can't Google these things easily, and we have little magic commands that will do some sort of local install. Let's do a local install. It finally killed off. And so this is one little fun thing in Python that you're running into at the moment. Is so currently Python 2 is probably one of the most popular Python versions around. But what's happening is that very slowly we're converting to purely Python 3. And so this means that all the major packages are now supported. So between Python 2 and Python 3, we switched from distutils to setup.py, and I didn't realize I actually pulled it off in Python 3.7, so there's a slight error on my part. So instead of just Googling Python setup.py, if you're in Python 3, make sure to Google Python 3 setup.py. Oh, first fresh versus small. The other thing is that you will quickly find that occasionally not everything is fully installed. So usually what happens is if you ever see I am failed to find sorry. those policies, this is something that you do not do too often, and there was a slight version compatibility issue. So before we had this line that was something like external packages of this utils. And for the purposes of this, we can actually just go ahead and delete that line entirely so that we move back to a simpler script. And so now once you delete that line and we run install-e one more time, I should get a successful install. If you do not get a successful install, please put up your hand and we'll come through and debug it for you. Okay, any other questions? Great. Okay, so now that I have this installed, what this means is that I did what's known as the local install. So whenever I change anything inside this folder, I can now access it from anywhere on my laptop. So for example, if I go to my base, my roots, I can now say import algebra. And I can do all of my operations that I would like to. And so in this particular manner, I've now actually built my very first Python package. I have created a folder, a single file inside, and I have added multiple functions to it. I've now installed this module, and now I can access it anywhere that is according to this particular Python installation. So, so now any kind of function that you put inside of this module, you can reuse inside of any other project. So for example, if you have scripts anywhere else, you can now say import algebra, just like any other Python module that you might find, like pandas and NumPy. And so in this, I did a couple steps. So I was looking for this magic pip install-e dot. And so where do you think is a good place to store this information so you don't have to memorize it? Yeah, in the README. Always a good place. So I might want to create some sort of section called installation notes. So if I want like a really big title, I do equals undersigned. If I want to do a smaller title, I do single lines undersigned. And so I can say, to install my project, run and so now what's nice is your README becomes a place that you can put all kinds of little notes. You'll find that READMEs of larger projects are really quite involved, but if it's just your own project, I encourage you to put anything that you would wish here. So for example, if you have like various design decisions that you made, like this is a great place to put it so that you're associated with this particular package. And the other little thing that we did is that I said pip install-e inside of these backticks. And again, when we put this on the website inside Markdown, this will become syntax highlighted. So it's up to you if you want to do the backticks or not, but it's a nice thing for the future when you're looking at it on say, GitHub or something. And so there's a couple questions about how this was laid out. You may or may not have tree, but if you run tree, you can see how we have this nested. So we have the README and the setup.py on the base level. And so the reason for this is these things are kind of like support for your actual Python package. So they are not internal in any way, but they are, for example, some notes that you want to keep for yourself or how to actually go ahead and install it. Well, everything else is going to be inside of this algebra, which is going to be the actual Python package. And so you can have your init.py, your operations.py, and potentially tens or dozens of others of files in here, depending on how complicated you wish to go. Okay, so instead of our algebra folder, what do we need besides just operations? What's another good thing that we want to do inside of algebra? Is algebra just summing and product?
Quadratic functions.
Quadratic function. Okay, we can do quadratic function. All right, so let's say we're doing something that's not inside of our operations, and so what we actually want is like not something that is used very often. I'm sorry, something that doesn't really go with operations, right? So if I think about operations, this is probably like all my addition, subtraction, product, factorials, you name it. But in this case, something like the quadratic formula likely stands outside of that. So in this particular case, I actually want to create one more file inside of here. And so there's a couple different things I can do with the quadratic formula, and we probably don't want to do anything too complex. And so in this particular case, I'm actually going to twist it slightly and build ourselves a polynomial function. That's okay. So I can call this as poly. And so one of the things that we had talked about before is the star args operator, which I think will be kind of appropriate for here. And so what my star args does is, I'm just going to go ahead and print this out real quick without going anything else. I'm just creating basically a blank function. And real quick, so to access this quadratic file, what do I need to do again? Insert my net. So now when I import my algebra, I can say algebra quadratic poly. And what I'm going to do is I'm just going to give it a single number like this. And so what I'm doing is, remember, this function has the star arg operator associated with it. And what this means is that I'm actually able to give this function an unlimited number of arguments. So for example, if I say 5 or 5, 3, 4, I'm able to expand this out instead of a tuple. So it's kind of similar to passing a list, but in this case, I'm passing my star args. And so inside of our polynomial function, so if I want to build myself a little bit of docstring so I can think about this. So for a polynomial function, what I want to be able to evaluate is something like this. Or some such. Do I want to offset shift? you know, like plus, or do we just want to go straight times x? It's a general question. It's things that it's always good to think about when you're writing these functions. All right, so plus a constant. Okay, 4. All right, plus a constant loses, so we don't do constants here. All right, so in this case, our polynomial function will not be a constant, so it will start here at x. And so if I think about my start args, what I could think about is maybe in this particular case, I have x, a, b, for example. Right? And so what this means is that the first thing that I put in is going to be x, the second thing I put in is going to be a, the third thing I put in is going to be my b. And so what I can say here is so I can unpack this, and I hope you find that this is probably not the best way to do things, but if you bear with me for another 10 minutes, I promise you we are going to start with this. So now that I unpack those three things, what I would like to do is go ahead and evaluate my polynomial. And how do I do this? Yeah, just in line 6. Yeah, so I can literally write I'm kind to myself, I'll go ahead and put parentheses around this. It's not needed because order of operations is carried out, but I find it just helps a little bit on the reading and understanding. And then I can return my f of x. Leave this up here for just a moment longer. So you can go ahead and call my function. And so let's evaluate 2 with factors 4 and 5. Let's do 4 and 2 just so we don't get too high on polynomials. So I'll print out that what I get is 2, 4, 2, and 16. So I went ahead and evaluated this. So if I think about this function, is this a good function or not? Is it easy to understand the input of? Is it extensible?
Only accepts 3 arguments.
Only accepts 3 arguments, so if I wanted to accept more or fewer, it would be nice if you could do linear, quadratic, cubic, etc. Polynomials. That'd be a good one. What else is not so good about it?
The order is fixed.
The order is fixed. Okay. But there's a couple ways we can look at fixing the order. What else is not so good? Just those 2 things? I think for me it's very opaque, right? Right, so I don't have a clean separation here. So I basically have, this order of numbers that depends completely upon basically my own intuition. So, somehow I have to know that this is going to be my x, and then this is going to be my polynomial part. So whenever I do these things, I kind of want to think through it a little bit, saying, what are better ways to organize this? So let's go back into our function and let's think about the first way that we want to fix this. So what's the most important thing out of those three things to fix first? And that's all relative. So basically, whoever states it first gets that problem fixed first.
The number of arguments?
So the number of arguments. So in that case, do you want to do higher polynomial expansions if possible, or something else? Okay. We have a ringing endorsement for this. All right. So I think one way to do this is, so for example, if I go back to my function and I think of it this way, and I can likely write a continued expansion out, right? So I can think of this as, I can do an ND polynomial. And so it's probably be good if my function could represent that ND polynomial. So since I already have a variable number of arguments, I have the technology to take different parts of that polynomial already. And I already have my x here. So perhaps instead of writing it in this particular way, I might want to write this in terms. And so what I can do is I can say that my coefficients is going to be args starting with my x and everything after my x. Have you guys done slicing in Python before? Great, okay. So I have all my coefficients, and I probably want to convert this to a loop. So let's just go ahead and say my result equals 0 to begin with. And I can say, so for C in coef, I should probably do something like result equals C times x. And if I think about this, the one thing that's missing is getting a polynomial on my x. So how do I get my x raised to the correct power? So for the first one, I should raise it to the first power. The second one, I should raise it to the second power, and so on. So what are a couple ways I can think about doing this?
The index of that coefficient.
So the index of the coefficient?
Plus 1.
Plus 1, right? Yeah, because in Python we start from 0. That's great. So how do we get the index of that coefficient?
There's probably index like a function.
Yeah. So I could do a couple things. Like I could basically ask like what that value is on it. But inside Python, there's something lovely called enumerate. So inside of enumerate, it's a Python keyword because if your syntax editor says loop. And so basically what that does is perhaps a better way of showing it is that for every single value inside of coefficients, so in this case the linear, the quadratic, what I'll do is I get the index of it automatically in my expansion. Have you guys seen this kind of unpacking before? See some shakes. Anyone know? Okay. So effectively, like this will return an index and my actual answer, and so we just unpack it so that power will range from 0 to n, and my coefficient will range over the ones that past n. Sorry? Okay. So If I do this, will I get my correct polynomial back? See, I see yes and no. So first of all, we said that we're not doing constants in our polynomial. And so we also know that indexing from Python starts from 0. So if I take x as 0, what do I get? Get 1. So that would be my constant shift. So at this point, I think I have a design decision to make. Should I allow constant shifts, or should I do something to effectively make sure that we're always going from the linear clump? So we have one vote for +1, so to kind of continue to linear out. Any votes for adding the constant in? Okay. We're at an incredible 1-to-1. Does anyone want to be a tiebreaker? Okay, let's vote it first so we get a power +1. All right, looks good, right? Okay, so let's give it a go. So let's be kind to ourselves and start with 1. And for example, if I give it 4, and I think through this real quick, this is linear, so we should just get a 1 times 4. Or that, excited. So let's add a quadratic term, 2. So in this case, because my x is still 1, I should get 6 back. Oh. That's really funny. Alright, so I get 6 back. And so if I continue on with a factor of 1, I should basically get the sum of all these things, which looks to be 22. And in fact, I get 22 back. So in this way, I think we're starting in on a kind of a nice function, right? And so what I'm trying to get at is kind of like this sort of like iterative process where whenever you design these functions, I think you will quickly find that if you design them to be extremely rigid, to only do one very small thing, you might end up with a bunch of them. Especially when, in particular, in this case, with the polynomial, it's rather easy to have your functions be able to be automatically extensible. So if you can think about this, the alternative case from doing something like this would be to have like a function called poly2, poly3, poly4, and so on, where I basically duplicate the code in every single time. So it's always good to think about how we can extend these things out. And if we do, for example, something like 3, we're going to get an extremely large number. I don't know what it'll be, but it should evaluate it without too much trouble. And you can think about extending this function in a large variety of ways. I could think about it, for example, not just taking a number 10 as an x. I might be able to take in like a list or a numpy array and be able to handle these things. I might also want to consider what about edge cases? So, for example, what would this return? I'm going to bet that it returns 0 or fails, and it indeed returns 0. So because we have no coefficients out on the end, there's nothing to multiply by, right? And so we said that in this particular case, I should just get 0 back. And it's worth thinking about, is this the kind of behavior that we want? You know, does this make sense for the polynomial? Some people shaking their head no. So if it doesn't make sense, what do we need to do inside of our function? A warning. Okay. Yeah, I like it. Okay. So probably the warning should occur at the top. That sounds good. Alright, so what am I looking for here? When should I throw a warning?
We're only including one.
Yeah, so it only had one input, it's not valid. And so in this particular case, how can I do that? How can I catch if I only have one input? Say if when args equals 1. Have you ever heard about exceptions before? Exceptions, yeah? A little bit. So whenever you throw an exception, you want to raise. And in this case, we'll throw a simple exception here. And so when we do this, this is a really nice way of telling our user, and our user probably going to be ourselves, that I did something potentially incorrect. And so this is a really nice way of catching bugs for yourself and trying to basically help yourself later. So what's a good message here? So while this is a factual statement, does this, if I can think about my future self, does this help me in any way? Not specifically. Because it says, like, indeed, it's only one, but what would be something that would help me? And I think in these error messages, you don't only want the statement of, like, what happened, but how can I fix it?
Specify x and coefficient, function means x. Coefficient.
You only entered
Value of x.
how that. So I think, like, if we thought about it, we might want to label it slightly more, but I think this is a pretty reasonable kind of first pass, because it says, like, you know, if I look into my function's help, I can see that, well, what I should be doing is writing a little more doc strings about how the first one should be x and the remaining one should be coefficients. But I think it's pretty reasonable. Okay. So now when I do this one more time, so now when I run it with 10, I get this nice message saying that indeed I've only put in 1, and I should probably look at fixing this. So as I'm sure you're probably aware that pretty much all major packages have this kind of feature where that if you try to enter something incorrectly, you will always hit some sort of barrier there. Okay, and so to be a little bit evil, what happens if I do this? Any guesses? You get an error. So in this case, the function structure itself has the error because I always try to access the first element, and because I have entered no args, I get something without any elements whatsoever. So at this point, you can do one or two things. It depends on how nice you want to be to users. So option 1 is saying, going back and having a if length equals 0, then you must at least have 2 values, accent coefficient. But I think at this point it's kind of worth discussing of kind of like what range does you intend this module for. So if you just intend this module for yourself, you might want to consider stopping at this point because perhaps you say that it's not worth it to me at least for the first pass. If I hit it a whole bunch of times in the future, then maybe that's something I want to go in and add myself a nice error message. If I'm going to do this for a whole bunch of people, and I want my entire lab to use it or a community to use it, I might want to consider like going back in and giving them a much more reasonable error message than the default 5.1. So I think at this point it's completely up to you on the range and scope of exception handling that you'd like to implement. So do we have any questions up to this point? Okay. Everything seems very solid, so that's great. So let's go ahead and take a 10-minute break. So let's be back, let's say 11:05, and we'll get started on the second half of this lesson. If you have any questions, please feel free to come up and talk to us about anything. Okay. So next up was we'd actually take our project and we put it on GitHub. Right. So if I'm doing little one-off scripts, then I think GitHub is perhaps like a little bit questionable. Like it could be useful, it could be not. It sort of depends like on your circumstance. But once you start developing modules, it's really a really good time to actually put these on GitHub, especially because, for example, I want to be able to share this. Right? So we discussed perhaps sharing these scripts within your lab. It's always good to put them up there because now you have a central location that people can go to instead of saying hey, navigate to this folder. Once you're in this folder, then copy this thing or whatnot. GitHub also gives you the ability to collaborate on these things, right? So say you build this really nice tool in your lab. One of your other members wants to hack on it. They want to do a little edit to it. Something like GitHub will actually make that a lot easier instead of saying hey, go edit this file on my desktop, and then if it breaks, go to the happens. So highly encourage you to push this in GitHub. And so to build a new repository, there is this big green new button if you go to GitHub. And I was told that everyone should have a GitHub account. Is that true? Excellent. Okay. So we click the green new button. And we get to call this repository something. And in this particular case, let's call it Algebra. I want a quick tool. So tool for manipulating. And so I'm going to make this one public. You should know that if you're an academic, you can actually get GitHub private for free. So if you want private repositories, you guys can actually have these. It depends on the work that you are doing, but you certainly have the option if you so wish. So one of the checkboxes is initialize this repository to README, and we're going to say no thank you, because we are good citizens and already did README. However, two things that I'm not quite sure that you've covered before. Have you guys gone over Get Ignored by chance? Okay. We'll actually talk about them in a second in that case. And we'll actually skip license for now. Just know that in general, that if you don't have a license, nobody can use your work. Technically, it doesn't mean that people don't use it, but it's they don't use your work. Usually, it really kind of depends on where you kind of land in your ends of these things. But typically for small open source projects that you're not really concerned with, licensing or anything like this, the VC clause is really nice. I usually like to start with it. Just because at the very minimum what it does is basically say that if anyone uses your project, they at least have to say it in their work, right? And it doesn't necessarily mean that you're going to be an author on their paper, but just whenever they write their own code, they're going to be hey, I pulled this and I used it. So it's sort of like a very minimal level of function. Okay. And I'm going to go ahead and go with a Python getignore as well. So you'll see that there's actually a couple files that Python generates that we do not want to add to our GitHub repo. And then go ahead and click New Repository. Okay. So we did a couple of things that could make our life complicated. So if I think about it, I have kind of history on my laptop, and so because I've been doing a couple things there. And now I actually have a little bit of history on GitHub because we made one commit to add these getignore and license files. So there's a couple ways of rectifying this depending on how enterprise you are. So probably way number one is that we take this and we download it and we copy everything over. And I think that's probably the most recommended way by far. The other thing that we can try is actually merging histories together. Excitement about merging histories? Not. Okay, all right. In that case, let's do it. Okay, so what I'm going to do is I'm going to go over here and I'm going to say git add my setup.py. Before I do git add, what's the very first thing I need to do in an empty repository? Git init. Okay, so I built myself a new Git repository, and so let's just go ahead and add everything. And I'm just going to create a couple of commits just so that we have like a little bit of history, but you can add them all in one fell swoop if you want. There's only a couple things that need a little bit of hesitant to add, and if you've added them already, it's okay. But this algebra.egg.info is actually a file specific to your computer, so you can distribute it. If you're in Python 2, you'll probably see these things that are like star.pyqc. And so Python basically generates these to make it faster to read these files in the future. So those are also very custom to your personal computer. So best not to add those as well. And then if you're in Python 3, you'll have something called this PyCache. And if you look inside the PyCache, you have the same POIC files. Again, it's very local and probably should not be added. Okay, so once we have added all of our files, and I'll give you a couple minutes to do this, we need to think a little bit. So basically we have one commit on GitHub, and then we have a couple of commits on our computer. Fortunately, we said that we did not want the readme, that empty, because if we said that, we'd have a conflict there. But I think the way that's currently set up will actually be able to merge without any kind of conflicts, and so it should be a fairly simple thing. So if I run my git status, I am on my branch master, but does this know anything about my GitHub repository at the moment? No, right? Yeah, because we haven't linked them. We haven't linked them together. So you guys know how to link these things together by chance? Sorry, should we git remote?
Sources.
I'm sorry?
I think sources.
Yeah, so we want to add another source, right? So we want to say that this file structure is going to be associated with basically some sort of remote. And so what I need to do is I need to go over to my own GitHub repository, and own, and I need to copy this line right here. And so in this case, I don't actually want to clone it, but what this does give me is it gives me the location of basically this Git repo on GitHub. And this is what I'm after, is where is it in the world. And so I want to go ahead and copy this line here. And the magic command that you want is git remote add origin link. And so in this case, what this remote is basically just a position of our location that I want to push to. So where do I want to get data? Where do I want to deposit data that is not on my laptop? Add is because I want to add a new remote. And origin is because I want to call it origin. So remotes are fun because you can call them anything that you want. I highly recommend calling things origin and upstream because that is what everyone else in the Git world will use as language. And unless you really know what you're doing, it can get really confusing. So git remote add origin. Okay. So now that I've done this, I have myself my GitHub on my local computer, and I have a little bit of history there, have some files. I also have the non-local one on github.com, which contains a couple of files as well. And so the first thing that I want to do is I want to pull those changes to my computer. So if I want to pull basically from that location, and the location is now origin, and also on GitHub, I want to pull from the master branch. So what is that command that I need to run to pull those changes from GitHub master branch to my laptop? Alright, so it's git pull. Are you familiar with the larger syntax of git pull? Like, do you know, like, git pull remote branch? Ah,
Yeah.
okay. Okay, so in that case, then we do need to do one piece of explaining. So whenever you do, say, like, just git pull or git push, what it does is it automatically decides, basically, that I want to push to origin master. So in this particular case, it knows the location that it's going to push to, and it already knows the branch that it's going to push. So git pull, git push can have defaults, basically. But in this case, because we have originated these two in kind of like a disjoint way, there is no default yet for these things. So always, when I say git pull, I can say what remote that I want and what branch that I want. So in this case, since we said that when we added this remote, we want to call it origin, we want to git pull from origin. And so in this case, again, origin is our GitHub account. So we are pulling from our GitHub. And then finally, once we do a remote, we also want to pull from master. Because if I look at my GitHub repository, the branch name is automatically master. Okay, well, that's good. That's fun. Oh no. Okay. Okay. Who got this message? Great. That'll work. Okay. So whenever you do a git, what it tries to do is do a merge. And because the merge basically requires a common history together, the two have comments. So in this particular case, what we want to do is actually a rebase. And what a rebase means is that I take from whatever's there, so I take all that history, and then I want to replay my histories on top of it. And so at this point, I do want to remind everyone that we didn't do the easy option of, pulling our GitHub repo down and just copying the files over. We decided to go with the slightly harder one of merging. So if you don't want to deal with this, which gets into a little bit of base Git, or more advanced Git. Always either start from a GitHub repo on the website and pull one down to begin and then build on top of that, or just simply copy the files over. Both those options are far simpler than this particular one, but I thought it would be kind of interesting to show how we can do kind of like these disjoint merges. So in this particular case, we had to default back to something called a rebase, and again, the rebase basically takes those commits and then place them on top. So I guess probably at this point,
Be on top, the local ones or the ones that are on the
so you assume that the master is the true history. So you pull that copy down, and then you play all of your commits back on top of that. And so if you remember, like each commit is basically like a diff, right? So it's very easy to basically play these diffs on top of each other as long as they do not have basically the same lines of code change. If you do have the same lines of code change, then it will pop up similar to a Git merge that you need to fix the conflicts. Like you manually need to go in and kind of rectify when two people touch the same bit of code. Okay, so at this point, probably a good question is, who does not have a license file? And who has not merged these things successfully together? Anyone? All right. So at this point, I should have complete history on my laptop. And so what I want to do is I want to push this back to GitHub. So when I want to push this back, can anyone think of the command that I need to run? Okay. So if I do git push, so at this point when I do a git push, it's going to tell me that indeed I have not set my defaults. And so Git is amazing and friendly, and it's saying that, you know, what you really want to do is run this. And what this says is that when I say set upstream, origin, master, I go ahead and set those defaults so that forevermore, whenever I'm right here and I pull and push, it will go ahead and use these defaults as we expect.
What if you want to push to a different branch instead of master? You don't have to set master as your default.
Right, so if you set something besides master as your default, that can be anything that you push. The one caveat, however, is that if you push from something called master and you want to push to a different branch, like on your node, what you have to say is git push origin master other branch. Yeah, so just a comment that if you try to push to different branches, you have to be very specific about, you know, I'm pushing from origin, and specifically I want to take my master and put it into other branches. Okay. So now if we go to GitHub, what I see here is that my Algebra package online, my git ignored here, which will prevent me from having to worry about these UIC files again in the future. Got my readme.md, my setup.py, and for example, you can see how those underlines and hashtags have translated to something nice, right? So it's not just pure text. When I go to GitHub, I get this nice markup syntax. And also, for example, like I have this pip install-e dot, and so I can see that it is doing a little bit of markup here, trying to indicate two. Oh, that's so interesting. So on my laptop, and hopefully yours, you should have this in a gray box, right? So I'm not sure what happened there, but perhaps the contrast ratio blurred it out, but very curious. But yeah, so anyways, you get this very nice syntax highlighting as well. Okay. So on the README syntax highlighting, let's do one more thing down here. So we have some installation notes, and what if we have something like user And so here we can say something like, this module can run products as shown. And so with just a small extension of the syntax, just so the 2 backticks will give me kind of like a highlighted gray box. But if I do 3 backticks for multiple lines of code, what I can actually do is I can show code in place, and if on the very first line I tell it that it's Python, I will get all the Python syntax highlighted. And so in this kind of way, I'm actually able to show code that's nice and syntax highlighted on my readmes and all my GitHub scripts. And of course, once you have done this, I would add it, commit it, and push it back up so that you can see the rendering on GitHub. And when you do this, you should get a nice kind of like pink reddish import followed by your numbers that are colored as well. This particular example probably doesn't take the full use of syntax highlighting into account, but you can probably imagine if you want to display something rather complicated, the syntax highlighting will be really quite useful, and certainly more than just straight text. And so I will not do too much more with GitHub today because I believe the session next time you meet will actually do a lot more about GitHub integrations. So just being on GitHub is really neat, and you can do a lot of things there with like communicating with people. But for example, I think next week we'll talk a bit about testing and like how you can basically run tests automatically using GitHub so that you can ensure that your code is always correct. So any questions on the content that we've covered so far? Anything in modules, even GitHub, anything like this?
So when you're writing like a module, how do you decide when to separate your functions into different files, or do you have a master file?
So that one's really hard, and I think there's no firm line of when to do that. If you have like a file that's getting probably more than like 500 lines, then you probably want to look at definitely breaking them out. But I think the best way to do it is like, do I have groups of functions, right? So, and what I mean by that is, what I try to do is like we have operators, so that's the entire class of things. So we have addition, subtraction, multiplication. Then I have my polynomials, for example, and that's not really an operator. right? So that's it's more of like it could, for example, use things in operators, right? And so you have those two ways of clustering things. And you also might want to think about what are functions that I want to use in multiple modules, right? So for example, sometimes people do some fancy things with print, right? So they want to do like color print, right? So maybe I want to make a util.py, put fancy color printing in there, and then I can have my other modules import that util and then the fancy color. So yeah, unfortunately, I'm not quite sure there's hard and fast rules there, but I think as you do it, you kind of get a feel of like when to split them out. And I think the good rule of thumb is that if you're more than like 400 or 500 lines, you should really strongly consider splitting them out, unless you have an incredibly involved package. Anything else? Great. So before we do too much further, I was thinking probably one of the things we might be interested in is doing command line interfaces. All right, so we have like all these nice functions, but I think a lot of times people are used to, for example, saying, kind of like my program, option 1, option 2. And so what's interesting is that after you actually have a module like this, it's very easy to write a command line program to it. And a lot of times what I see is like someone has built like a complicated way of manipulating an image. And so what they'll do is they will add a command line program to this so that whenever they're anywhere in their file structure, they can say like, alter image 1, save it to this one.out or something like this. And so it makes it very convenient to quickly run scripts and so instead of saying as well, like, Python script.py with a couple arguments at the beginning, you can kind of formalize this thing quite a bit. And so to start, and I wouldn't follow me, I'm just trying to do like a little demo right now. There's something called sys and sys.rb. And so what sys.rb tries to do is it attempts to capture what are all the argument variables that I started to find. And so when I run this real quick, what I can see is that I get basically whatever my first name was, and then whatever all my arguments are. So this one's always nice because it tells you, what file it was run from. Well, I can have an arbitrary number of argument factors. And so there's more complicated ways of parsing arguments, but I think for right now, like this is nice and simple. So basically, every single thing that you type after your command line is going to be presented here. So I wouldn't quite call this yet, but you can imagine, for example, like if I want to say do something simple, and I want to basically compute my product, right? So. I can think of like a very simple unpacking. And then I might usually do something like this. Right, so what this will basically expect is I need to type Python temp.py, command 5. I'm going crazy when I'm doing around. Operations. I'm really excited because it's going to be my first command line program, and then I hit something like this. So, is this kind of an expected outcome? So basically it's telling me that like 4 and 5 are strings, not integers or floats or something like that. So I think this is actually a pretty expected outcome. Because whenever I have these arguments here, I'm not actually able to determine their types. So I don't know if they're ints or floats or anything like that. And so natively, I'll always get errors like this. So we can think of one way to fix this is very simply saying int on both of them. And so now when I run 5 times 10 4 5, I now get 20 back. So and this is when we have to be really careful. It's like we have to determine like what our types are up front. So for example, like what happened if I did 10.5, 4.5, and 5? In this particular case, I'm kind of limiting myself. So usually on command line arguments, I don't really do as much integer and float manipulation like this. Very often these things are almost always strings like file names or the like. But I did want to point this out as kind of a caveat. And since we do have a math-heavy library that does no string manipulation at the moment, we will be having to pass these for these examples. And so in this case, let's start building our command line program out. So I'm going to go into Algebra. I'm going to copy my key over. I'm going to call it CLI.file. And so CLI stands for Command Line Interface. You see a lot of programs will either have a CLI.py or actually a CLI folder. They have multiple CLIs to export. But this is kind of one of the canonical ways of starting to approach this. And so effectively all that I really need to do is turn this into a function. And inside of CLIs, usually what you do is you call these things def name. I'm going to do it in such a way that we go ahead and capture the result in this fashion. And usually when I'm doing a CLI, what I want to do is something kind of nice for my users. And so I might say something like, product of so in this particular case, there's absolutely no harm in basically showing what arguments we're going to put in. In fact, usually, doing some sort of like little short demonstration of what was inputted and perhaps progress or something like this is always advised. So in this case, what we want to say is like, if we did 4 and 5 again, the resulting error message would be like, product of 4 and 5 is 20. So it's a nice, concise, but very explicit message, giving the user everything they need. Did anyone see the syntax error? Okay, great. So so now the question is, how do I actually get at that CLI? And so, for example, like if I type Python and I say, oops, sorry, I added the CLI, there's one more thing I need to do. So before I can actually manipulate it.
Sorry, add it to the init.
Always add to init. And so now if I say Python import algebra, algebra.cli.main, there, like this, I'm going to get some complaints because, of course, I didn't really add any arguments. So whenever I use CLIs like this, there is a bit of a downside that they effectively need a little bit of hand-holding in order to get to where we want. Fortunately, Python has this thing called endpoints. And so an endpoint is basically I'm able to run a function inside of a module from some sort of command line. And so what we can do is we Google Python 3 endpoints. I don't think there's a perfect one. Oh, there was a perfect one. Yeah, command line and environment. And hopefully inside of here somewhere they will actually give us the necessary commands, but unfortunately it is not. So I feel very bad because whenever I do like Googling and trying to show people like how to do these things, it works out like basically 99 out of 100. And so far we're batting 0 out of 4 today. So I very much apologize. I'm not sure what's going on with my Google skills or what's happening, but somehow I'm failing there. So perhaps like Python 3, web APIs. No. So this is the one that we're really looking for. And unfortunately, it was a little bit varied than I really wanted. But it's effectively what we're after is this endpoints, or what do they call them? Entry points. But effectively, we can see that this is one more little piece inside of our setup.py. So if we go ahead and take this guy and copy it, go to our setup.py, add it at the bottom. And so what I see here is that in this case they have unused-joke equals this function. So in our particular case, what we want is we want perhaps like algebra-product, because this will be the name that we call from the command line. Operation. Oops, and that's not even it. I want to do algebra.cli. And so effectively using the syntax, what this will do is this will map some sort of command line program, so algebra products, to the function algebra CLI. And so algebra.cli will get you to the file, and then we want to call the main function. So I have no idea why they decided to go away from dots and went to dots and semicolons here. That's just the way that they decided to do it. So therefore, we have algebra.cli get us to the file, and then main will get us to our perfect function. And so once we have done this, we do our pip install -e one more time. And so when I run my algebra product, I get the product of 4 and 5 is 20. And so if I think about it, in this way, I can go from just having scripts to actually having these command line programs that I can execute anywhere. And what this will do is this will give me a lot of possibilities for flexibility. Like I can have options that I can specify the command line to do different things. I really like this image example because I know someone who they basically has individual slides of an image, and they can get them back out in grayscale, or they could adjust the contrast or the light on the fly. That was very domain specific. They even got to the point where they took the image, they ran it through scikit-learn to find individual features inside that image, and then use it to highlight those. So you can go, from simple things to just make a couple little operations a lot easier to something that will impact your research on a daily basis, depending on how far you wish to go with these things. So hopefully this gives you kind of an overview of modules, CLIs, and how to do a couple of different set of ideas.
I did say algebra dash product notation was renamed
Yeah, so
function or
if I just look at my console script, I see what I'm doing is I'm saying algebra product equals something. So whatever is on the left-hand side of this equals will be the command line argument that I call. And then again, function file, files then. Okay, so any questions about command line utilities? So this was meant to be a pretty quick overview of them, but happy to go a little bit more in detail if you wish. So now I want to talk just a little bit about clean code. And I would have copied out. I'm making a little bit of point. And so what I'm doing is I'm writing a little bit of gibberish here, just to make kind of a point clear. So you may have noticed that I did a lot of different kinds of spacings, and I made sure that different things were aligned and this kind of thing. And so you have a lot of different options on how you can write your code. And so this is actually completely valid Python. This will work. But I think it makes it extremely difficult to read. The other thing is, and you can build a ton of examples, and actually I won't go too much more into that. But effectively, like how you write your code actually matters quite a bit. Not only to you trying to read it, but in the future if you want someone else to pick it up. If you think about like this kind of code versus something that I was typically doing, if you have this and then everyone does it this way, then the cognitive overhead of understanding like something like this is lower. But if you have like kind of different ways of doing spacings and organization, whenever I have someone looking at the piece of code, the cognitive overhead is really quite high. And so if I think about all of this, the Python Software Foundation actually came out with a canonical way that you should be formatting your code. And it's something called Type8, and it's the style that I have been writing everything with. And so you can read about Type8 if you Google, oh hey, I finally worked out. First result. And what you do is you get maybe like 50 pages of stuff, which is more tedious than I think anyone should really have to follow with. Fortunately, there's something called formatters, which basically do automatic application formatting for you. So there's a couple of them out there in the world, and there's stuff like there's Black, Flake, and Yap. And personally, I've kind of come to like Yap over time, but pick it whichever one that you want if you wish to go this way. So for example, if we want to use Yap, Yap is from Google, and it's called Yet Another Python Formatter. And so if I just do pip install Yap, what I can do is I can yank it from the internet real quick, have it on my computer, and then to do that, I'm completely ready to go. It's very nice and lightweight module as well. And so if I look at my rough NumPy, and versus if I run it through Yap, what I can see is that this was a fairly simple example, so there wasn't too many changes to make. But what Yap will do for me is automatically apply all of the style syntax. And so in this way, you can get basically canonical looking code. And usually, like whenever I'm writing code, like I might miss a space somewhere, I might have too many spaces or something like this. And just like little mistakes all over. And what Yap does for you automatically is cleans it all up. So I really like it. I think Yap and style formatters are overall a really good idea. If you use the command line, you can use it like this. If you, for example, use some sort of IDE like PyCharm or the like, they have formatters integrated into them, so you can use these as well. You can even use Yap instead of PyCharm to rely on like you wish. But overall, I think that they're very quick and very useful thing to do. And so, for example, if I say yap-I, which means in place, it will actually just go ahead and fix my file. So now if I have it, I'm able to basically yap in the individual files automatically, and I can also do, I think I need one more argument. Yeah, I think I want R. So if I want to yap an entire directory, it becomes very easy to do as well. I just say, I-R, do everything for me. And the great thing about it is you no longer have to worry about this thing. Right? You don't have to worry about formatting. You don't have to be like, oh, did I get this thing right? It cleans it all for you at the end of the day.
Does this accidentally break her code?
So I wouldn't say the app is guaranteed not to break your code, but I've been using it for 5 years and it's never broken my code.
Okay.
And this is like doing Yap on. So I think I encountered one program that was like so terrible that was something like 55,000 lines of Python, and I couldn't read anything. And I just yapped the whole thing, and everything was fine. So I wouldn't say that it won't break your code, but it's extraordinarily uncommon. Yep, it's a big fan of Yap. And you can see that, for example, I'm just looking at the git diff real quick. So sometimes, like, it had too many spaces between functions, so it removed those. Sometimes it didn't have enough spaces, so it added them. And so overall, it goes through and doesn't only just do functions and spacing, it makes sure that you have all these things right, mixes indentation. If you build nested dictionaries, for example, like Yap is phenomenal for actually transforming them so they can make you able to read these things. I think in something like Pandas, sometimes you often get a function that takes a whole lot of arguments. It actually formats all these things nicely by putting them in columns. And sometimes I think you might be surprised about what Yap does, but ultimately Yap is kind of industry standard these days. So it's usually just to let it do what it does, just kind of accept whatever the results are. But just note that if you wish, you can turn Yap off on individual functions or individual Python dictionaries by saying Yap disabled. And I can show you one, but it is probably best just to look up the documentation. It's just one.
Is it just about spaces, or does it change the names of variables?
So it won't change the names of variables. And actually, that's a really good point that I haven't talked about yet. And actually, I was going to do this for I forgot. So in Python, there's kind of a standard way of naming things. And so the overall idea is that you do something like state case for all functions. And so what snake case means is that I'll have my underscore new function, all lowercase. And any kind of class that I have is going to be something known as camel case. So I don't think we've gotten to classes yet, but if you ever see a class, they'll be in camel case. A good example of this is like data frame or series in pandas. Both of those are classes, and if I think about data frame, it looks like this. And a series, so they're all classes. And so what this is able to do is actually, if you see something that's camel case, in general should be a class, and so you're able to interact with it in such a way. And if you see snake case, you should expect that it's a function, and you should be able to interact with it in that case as well. So something like yap will not fix this for you. So yap is purely stylistic choices, and stylistic choices not including nomenclature. So yap is really great, but it is by no means complete. So let's go ahead and add our CLI. And go ahead and push that off. I could add ref if I wanted to, but it's kind of just a demonstration file, not really part of my project. Alright, so at this point, I think I've blazed through the contents that I really wanted to get through today. So I was thinking if you wanted, I could do a couple other things if anyone has suggestions on things that they're looking at or wants to know anything.
There were a couple of other things that you suggested we can fix in the polynomial function.
Okay, so I think your polynomial function is pretty decent right now. What else do we want it to do? So one kind of neat thing that we can do actually is we can do something like this. Where basically I'm guaranteed to have at least one argument now. And so I can remove this part of it, because what this is saying is that my very first argument is always going to be x. It's not going to be a variable x defined by function. And then everything after that is going to be my polynomial coefficients. So now this actually simplifies my code quite a bit, because I can delete this line, and I can also effectively delete this. And so if I just rename this to coefs, my function now should behave exactly the way that it did before. But now I don't need to catch it if I have 0 arguments, because it's going to say at least one argument is required. And I also need to change this line to be now we need to check that it's not 0, because if it's 0, we add no coefficients. And we could say you've not provided any kind of polynomial coefficients. And so I think just a couple of little tweaks on this function actually makes it quite a bit easier to interact with. So now x is effectively, or the very first argument is now labeled, and is always my variable that I'm going to expand upon. And also my coefficients are now contained so that I can do kind of specific things related to them. So now if I import algebra, so if I say 10, I get a nice error showing that I've not provided my polynomial coefficients. If I enter 0, it's telling me that I have not entered the one required argument x. So in this fashion, I should have Python automatically do that check for me. And I introduced a small button. In quotes, not in quotes. And so now, when I run it, I get the exact same behavior back, but I think we have a bit higher control over exactly how everything runs. So in the capital file real quick, in case you wanted to relook at this interest. So after we mess with this a little bit, I think this is actually a pretty decent looking function overall. And so one actually cool thing about the function as we have written it, it's not quite true. So how big of users are you guys of like NumPy or Pandas? Is that high on the list, low on the list? See some not NumPy? NumPy or Pandas? Okay, 6. All right, well, that's good. So let's look at how we can modify this ever so slightly so that it could take both a NumPy array in and a single value. So first of all, have you guys heard about Python's duck typing? You guys know what duck typing is? So duck typing is a very profound concept that goes like this. If it looks like a duck and quacks like a duck, it's probably a duck. So the point is that Python really has no types at the end of the day. So if I have something, so for example, if I have a float or an integer, it works in here just the same way. Because Python knows how to take a float and multiply it by a float and an integer and multiply it by an integer. And so in this particular context, integers and floats work out exactly the same way. And so what we want to do is extend out our code ever so slightly so that we can actually do this with NumPy arrays as well. All right. And so all of this right here will work just fine. All right, this line. But the real problem is the result equals 0. When we have result equals 0, we're saying that a result must indeed be this particular thing. So there's a couple of different ways that I could do this, but probably the easiest, honestly, is just x times 0. And so if I think about this, if I have an integer and I take it times 0, I get 0. I have a float multiplied by 0, 0. If I have a NumPy array and multiply the whole NumPy array by 0, I get a completely 0 array back. So in this particular case, it was actually extraordinarily easy to alter to be able to do this. We will pay an ever so slightly larger amount in terms of costs because the Python actually has to interpret the times 0 for integers and floats. But overall, like, we're not too concerned about that, I don't think, because it should be a fairly small cost overall. So with that very tiny change, let's see. You might have to go grab NumPy. I realized I started a completely based repository. So now instead of x being a single number, we're going to say is np.array, I don't know, say 10. And so a range works just like range effectively, but instead of giving back a list of values, actually gives back the NumPy array value. If you're not familiar about NumPy is great for numerical and linear algebra, simply because the way that NumPy works, it is going to be between 10 and 1,000 times faster than canonical Python. Also, one of the nice things about this is that you have something called broadcasting. So if I take like x times 5, for example, what that will do is it'll multiply every single element in my numpy array times 5. Or if I want to do something like x plus x, it will, instead of saying every single element times 5, it will take it element-wise and add every single one together. So if you're doing a lot of numerics, it's just looking into this. And this kind of broadcasting ideas and syntax is very similar to something like Canvas as well. So this idea is sort of proliferating throughout the Python ecosystem. So now if I say, for example, import Algebra, cool. So I have, I think, significantly enhanced the flexibility of my function if I need, for example, numpy and float support. By thinking about this just a little bit, and I'm able to basically have this really nice extensible function. I can do all kinds of new things. And with NumPy, what's crazy about NumPy is that I'll be able to do something like this. So instead of having just a single 1-day one, or 1D one, I can actually do a 2D one, and it all kind of works out still. So I can gain really a lot of flexibility by thinking just a little bit about allowing something like NumPy support. And of course, if I go back and say that now you are 4, I should get 120, I should get 200, yeah. And so I can recover individual results, I can get broadcasting results. And for example, if I want like a float, it all works out great.
I don't have last 5 at 0, x times 0 is a requirement for manifest.
Right, so if I didn't do x times 0, for example, what I would get is something like, so otherwise it'd have something like this. I'll do this. Actually, it's really surprising it works. So that's kind of interesting. So I actually wasn't aware that it did left-hand side broadcasting as well. But I think the no. I didn't know you could do that, honestly. That's a little bit surprising from a computer science point of view because you're basically mutating the side from the left-hand side, but apparently it works, so we didn't need to multiply by 0. I developed NumPy, I didn't know this part. Yeah, so apparently didn't need to do it, and it all works out.
Complex conclusion that can be covered with NumPy just by trying, or are there differences in syntax?
Yes, I mean, usually like the NumPy, like a lot of the broadcasting stuff is very deductive. So for example, like, if I have a value times array, it kind of makes sense that I want to do that operation on all of the of them. If I have like array times array, I can do it element-wise. I can also do things like so x plus b. And so what this will do in this case is, if I think about x dot shape and b dot shape, so the shape of x is 4 by 4, while my shape of b is 4. And so I assume that on the left-hand side, it's basically all 1, so I want to broadcast to the left. And effectively what this means is that my shape could be not just 4, but 1 comma 4. And so what this means is that this is what's known as C-contiguous, and I apologize for going quickly through this. But so I have 4 rows, so I have 4 columns. And so if my shape is 1 by 4 here, what I want to do is I want to add 1 through 4 to every single row in this matrix. The NumPy documentation has a lot better description of all this by far, and they're able to walk you through it. But overall, using these broadcasting ideas, you're able to do a lot of really powerful mathematical operations. And what's nice about NumPy is they're all fast. And so again, it's basically kind of like pandas. If I do individual operations, it's pretty slow. But if I operate an entire column or entire data frame all at the same time, it's going to be much, much faster. Any other questions that I can answer?
One question on broadcasting. So when do you have to add new access? You can't only broadcasting, right? You have to access information.
Sure, yeah. So what we do here is that we kind of assume that, like I said, we always assume to like the left. What happens if we want to add 1 through 4 by columns, right? So I want to add 0, 1, 2, 3 across all of these. So in that case, what I need is I need to reshape this so that so again, by default, I always assume that there's a 1 to the left. But if I add a new axis, which is explicit as none here, I'll make it a little bit opaque, but it's very common in NumPy. So what it's saying is that I want all of my values along this axis here. So I took my 4 array, so I reshaped it this way, and then I'm only going to need 1 width. So when I do this, effectively I get out a column right here. And so now when I do A plus B, sorry, X plus B, and compare that to X, I can see that, for example, I added 3 to this entire row to 1 and 0.
So what if you multiply x? It's going to be
So it's exactly the same thing. So instead of adding, we will in this case multiply. So in this case, we multiplied the first row by zeros, the second row by 1, so we get the exact same thing back. We doubled this row and tripled this row. And so things like division, even something like powers work like this. So any kind of mathematical operation can be broadcasted.
How is this different from vectorizing?
So NumPy is completely based on vectorization, right? And so you said an R. Oh, yeah, it's vectorization. Yeah, so in total, like something like pandas and NumPy together aims to effectively do everything that R can, but involved in like the Python ecosystem. I definitely wouldn't say that they're there yet, but that's sort of the intent behind where those two packages are going.
So one of the difficulties I had with migrating for on Python is getting data into Python.
What kind of data do you have? So what is that format?
Rectangular format. Rows can be deep and columns can be individual observations.
That means like a CSV file?
CSV.
Okay. So CSV, you probably really want pandas for something like this. So, for example, I'm going to say CSV. So just for example, just something very quickly. And so if I have pandas, usually import pandas as PD. So we just say read CSV and then call the encrypted CSV. So any kind of canonical file format can be easily read by pandas. You can read Excel files, HTML5, CSV, JSON, you name it, about there as well. NumPy is a bit more limited because it does focus more on numerics, but you can do things like load in like binary arrays and stuff like that. So it all kind of depends on where your focus is. And what's nice about pandas is, for example, are you guys familiar with Jupyter Notebooks at all? So you get my data frame there, and so for example, if I want to just look at like header 1, I want to plot it. Again, very quickly. Or I can do multiple line plots. I can do just to give you an idea, so if you read these like into pandas, you can plot them easily. It is kind and so you're able to kind of like switch out different graphics and get them labeled in various ways. And so, for example, if that's not enough for you, there's a really nice library called Seaborn out of Stanford Statistics Department that you can do some really, really cool things with. For example, like going to do like swarm plots, it integrates really nicely with pandas. So we do swarm plots very easily. And then everything in between, so you have like cluster maps, nice scatter plots where things are rated points. So basically anything that you can really think of or desire in terms of statistical plotting, Seaborn really kind of has you covered. So yeah, kind of going off a little bit of a tangent there, but even stuff like heat maps as well. And so, in a lot of ways, I think usually starting with stuff like NumPy, Pandas, and Seaborn will get you covered on a good chunk of data analytics within Python. So if you're looking at like individual issues of Alicefish, usually googling something like Pandas, like how do I read this thing, will give you some sort of answer. Hopefully your luck is better than mine today, but it almost always is. Any other questions that I can help with? Last couple minutes. Well, great. Thank you so much for coming out. I really hope that you enjoyed this and got a lot of value out of this. And I'm curious to see where this kind of course goes in the future. So, yeah, we'll see what happens over time. All right. Thank you very much.
Thank you.